Okay, good morning. So, this is our last lecture, and today we will continue our discussion on the flow past immersed bodies. And in particular, if you recall, yesterday I discussed the case of a cylinder. For the flow over a cylinder, if the flow conditions are laminar, then we will be having separation at about 82 degrees, and if flow conditions are turbulent, then separation is happening at about 120 degrees. And this is the reason that in case of this we will be having larger drag. That's why drag coefficient is close to 1.2. On contrary, in case of the turbulent flow where separation is happening slightly later, our drag coefficient is actually significantly small in comparison to the corresponding laminar case. Okay, one important point I would like to highlight over here: yesterday we discussed that this dash line, whatever we are getting over here for pressure coefficient, this is based on the inviscid theory. Okay, so if we consider the inviscid theory, then what happens for incompressible flow situations? Pressure at this point and pressure at this point will be the same. Okay, so because of this, the front pressure distribution and the rearward pressure distribution will be same. And if pressure distribution is same on both the sides, front side and the rearward side, then we will be getting our form drag to be 0. Okay, so form drag is 0 as per inviscid theory. And if we are considering the inviscid theory, then ultimately we will not be having any skin friction drag. Okay, because skin friction drag is mainly originated because of the shear stress, and shear stress depends upon the viscosity. Okay, so if we say that we don't have the viscosity present in the system, then our skin friction drag will be 0. So ultimately my total drag force will be equal to 0. So this is not reality. This is not a real situation. That's why this type of paradox, which gives us the zero drag force, that is called as D'Alembert's paradox. Okay, so as per D'Alembert's paradox, if we have any symmetric cylindrical or spherical body, then we will be having the same pressure distribution in front side and the rearward side, and there will not be any skin friction drag. So form drag will also be 0 because of the symmetry in pressure, and ultimately we will be getting 0 drag, which does not happen in reality. That's why it is called as D'Alembert's paradox. And particularly if I apply this even this theory uh, for inviscid theory for compressible flow situations, once my Mach number is greater than 1, then this situation does not occur, because then the drag which is coming because of the pressure distribution, that can be 0, but the drag which is coming because of the presence of the shock wave, that will be coming into picture. So that's why D'Alembert's paradox does not help, does not work in case of the compressible flow situations. But in incompressible flow situations, the situation of zero drag by considering the inviscid theory is something which is not practical. That's why it is called as D'Alembert's paradox. Okay, now this is the case of a flow past sphere. So in both the cases you can see this first case is corresponding to a laminar situation, and second case is corresponding to turbulent situation. And you can see when a spherical ball is actually moving downward in a liquid, here also you can see that for laminar flow at theta close to 80 degrees flow separation is occurring, whereas for turbulent flow this is happening at about 120 degrees. Okay, now one important point why we need to do streamlining. So if I have, say, this type of cornered body, then I will be having flow separation at this point, at this point, and this point, and we will be having very high drag coefficient. On contrary, if I make this front portion rounded, then there will be significant reduction in the drag, and I will be getting CD close to 1.1. So you can see there is, by just making this front round, we have about 45% reduction in the drag. Okay, then if you also mix this rearward end also a little bit tapered like this, then you will be having further significant reduction in the drag, and drag coefficient will comes out to be close to 0.15. Okay, and if you consider equivalent cylinder for this drag force at the equivalent conditions, then this cylinder size is very, very small. So it means that streamlining is something which helps us in reducing the drag force by significant amount. That is the reason, if you see the body of this aeroplane, okay, so you have some structure, something like this. So this is nothing but a streamlined structure. Okay, because we have significant reduction in the drag. Then these are the drag coefficient for different smooth bodies. So here you can see if you have a smooth flat plate which is parallel to the stream, then this is how drag coefficient varies. Then if you have a smooth circular cylinder, or if you have square, then what are, or if you have some flat plate which is normal to the body. So these are different drag coefficients. Even for some of the birds also drag coefficients are quantified over here. So for example, for pigeons this is the drag coefficient, and for airfoil this is the drag coefficient. So it means you can say that the present day airfoils are even more efficient in comparison to the birds, because birds are having higher drag coefficient in comparison to the airfoil structure. Okay. Then similarly, if we have to see the drag coefficient for three-dimensional objects like sphere, so you can see for sphere our Stokes law is applicable, and in laminar flow conditions CD is nearly equal to 24 by Reynolds number, but that is applicable only for creeping flow conditions. So now what are creeping flow or Stokes flow conditions? Okay, so the condition where our Reynolds number is smaller than 1, that particular condition is something which is called as creeping flow and Stokes flow condition. Okay, so typically in a creeping flow condition we will be finding that there will not be any acceleration, significant acceleration of the fluid. So that's why left hand side of the Navier-Stokes equations vanishes, and we are simply having only the viscous shear term and the pressure term. Okay, so if we solve the viscous term and the pressure term, then ultimately we will be finding that CD is 24 by Reynolds number, and we will be also finding that drag force is equal to 3 pi mu RV. Okay, so this is the drag force for sphere under the conditions of Stokes flow or creeping flow when Reynolds number is less than 1. So the beauty of creeping flow is that its solution is easy to determine. Why? Because the acceleration term, the left hand side of the momentum equation completely vanishes, and the viscous term is simply equal to the pressure gradient. Okay, so this is identical to fully developed laminar flow in a pipe. So now we have different two-dimensional bodies. So depending upon the orientation and direction of the flow, you can see what will be the corresponding value of CD, and whenever this CD is defined, it is written in this table that this CD is based on the frontal area. So it means once you will be using this CD to determine the equivalent amount of drag force, then you need to multiply your CD into half rho V square multiplied by frontal area. Okay, so this type of tables will be provided to you. I have given over here so that you can get familiar with the tables. Okay. Then this is also again some two-dimensional shapes, and these are some three-dimensional shapes. So how CD varies for different three-dimensional shapes, that is actually given over here. Okay, so you can refer these tables once you find the questions related to these type of shapes. So obviously what you need to do is practice, okay, before coming for the exam. Then this is a typical representation of aerodynamic forces which are acting on road vehicles. So you can see how year by year this evolution has taken place. In close to 1910 to 1920, this is how our shape of the road vehicles used to be there, and corresponding drag coefficient was very high, about 0.8. Then people have thought of having some streamlined shapes, and then you can see year by year we are getting more streamlined cars, and our drag is further reducing. So if drag is reducing, it means engines will be taking the less power, okay, because engine has to overcome the drag in order to propel the vehicle in the forward direction. So you can see now the present day streamlined bodies which can give the theoretical minimum drag close to about 0.15. Drag coefficient is about 0.15. Okay, so this is how the evolution has taken place. So maybe you can think that still we are having this type of cars where drag coefficient is close to 0.35, but in some of the sports and racing cars, there you can find this theoretical minimum is actually kind of achieved. Okay. Typically, one important point is called as, that is the upsweep, which is provided at the rear face of the automobile. So this upsweep angle is very, very important. If upsweep angle is close to 25 degree, then we see that the downward lift force which is generated on this body is actually highest. Okay, why downward lift force is required? Downward lift force is required on the body if you are moving on a slippery road. Okay, so then what you need to do, you need to create a traction force. So traction is nothing but the friction force which is generating between the wheels and the road. Okay, so that friction force will be proportional to friction coefficient times the normal force. So if we are able to achieve this more magnitude of downward force, then we can achieve actually traction. So that's why sometimes this sweep angle you will be particularly finding in the vehicles which are designed for the off-terrain roads where traction is actually needed more. Okay, and corresponding to upsweep angle of 25 degree, you will see the highest downward force which is acting on the body. Okay. One important point, so you can see nowadays if you are having bigger trucks, so in earlier days trucks used to have less powerful engines, so because of that their speed were not that much high, but in the present day trucks are also having the high speed motion. So because of that, if we consider the relative comparison of the rolling resistance between the tires and the road, then this curve is something like this with the vehicle speed. But if I consider the air resistance, then it moves something in a parabolic fashion. So corresponding to this, whatever the gross engine horsepower is needed, so this is the curve for gross engine horsepower. Okay, so it means that when the truck is moving at high speed velocity, so we are having parabolic increase in the power requirement of the engine, so there is need to decrease the drag. So one of the efficient way which are being tried is the front face of this truck is provided with some sort of deflector, and by adjusting the angle of the deflector for different speeds, flow can be oriented in such a way so that it does not interfere with this corner but passes smoothly over the body of this truck. Okay, so these type of arrangements are also very much necessary for high speed trucks and are being used in the recent days. Okay. Then along with the drag, another important force we discussed yesterday was lift, and lift is also very, very important, and particularly the importance of lift we see in aerospace applications. If you have aeroplane, then you need to fly aeroplane. So once you have to rise from the ground to the desired height, then you need some upward force. Okay, so that is something which is a lift force. And second important point, we have seen these nowadays this hydropower is very, very prominent. Okay, and it is taking over now the other conventional sources of power generation such as the thermal power plant, etc. Okay, so in hydropower we have these turbines. So the blades of the turbine we want in such a way so that they can generate the maximum lift force and minimum drag force. Okay, so wherever we are having requirement of lift, our requirement is we should have minimum drag and maximum lift force. Then only we will be able to utilize the power of fluid in more effective way. Same is the case with the wind turbine. So you can see that in wind turbines also, the blade of the wind turbine is having some sort of this aerofoil like structure. Okay, similarly even the this Francis turbine and Kaplan turbine, whatever are used in hydropower plants, their shape is also actually blades of these turbines are also of streamlined shapes. Okay, so this is a typical aerofoil, and here you can see that this aerofoil is having this front end to trailing edge distance which is called as chord, and this width is called as span, and these are the forces, and whatever the angle made by chord with the direction of the free stream, that particular angle is called as angle of attack. Okay, whenever we will be talking about this, so we have to calculate two different quantities. One is lift coefficient, another is drag coefficient, and both these coefficients over here for the aerofoil structure are defined based on the plane form area. Okay, because this is nothing but a streamlined body. Okay, so for streamlined body, our plane form area will be coming into picture, whereas for blunt bodies, we majorly rely on the frontal area. Okay. So here you can see how the generation of the lift takes place. So this is the very first stage. When flow immediately starts happening over the airfoil body, you will be finding that flow bends at the backward side and there is no lift generation. Okay. After subsequent progression of the flow, you will be finding there is formation of a vortex, and this is the point where very small amount of lift will start originating. And once this vortex trail keeps on extending, then here you will be finding the formation of chaotic wake. Once you have the formation of chaotic wake, you will be finding in the upper portion you have lesser pressure in comparison to the pressure at the bottom face, and in this zone you can say that you have the highest formation of the lift. Okay, so more you are away from, more this vortex tip is away from the body, you will be having more chaoticness over here, and the maximum amount of lift will be generated in order to lift the body in the upward direction. Okay, and this is the typical condition. So here you can see this angle of attack was very small. When the angle of attack is large, so you can see this is now the chord and this is the flow. So this angle of attack is very large. So once the angle of attack is very large, you can have this flow separation point at the starting edge nose of the aerofoil itself, and in this type of situation you will be having huge amount of flow separation bubble, and because of the presence of this flow separation bubble you will be finding that there will be suddenly the value of lift will become equal to 0. Okay, or suddenly the lift will decrease. So this type of condition is called as stalling of an aerofoil. Okay, so whenever you are generating a lift, obviously you have to maintain optimum angle of attack, but if your angle of attack is very large, in that case you will be finding that you will be having highest amount of drag force, because majority of the flow is now being restricted, and in the backward side I will be having very low pressure zone. Because of this there will be significant amount of drag force, but lift will immediately becomes 0. That is called as stalling of the aerofoil. Okay, so these are the coefficients, lift coefficients and drag coefficients for different aerofoil conditions, and you can see clearly this point is nothing but corresponding to the stalled condition. After this point there will be sudden fall in the lift. Okay, so these are typically, if we have to improve the performance of the aerofoil, then people have tried different types of flaps. So for the aerofoils of different flaps, so if you when you take aeroplane, there also you will be finding that in the body of the aeroplane some sort of flaps are provided, and then depending upon the landing and the takeoff positions we adjust the positions of these flaps. So you can see these are different values of lift and drag coefficients for different types of flaps and for different degrees of flap angle. Now depending upon our requirement we adjust the value of the flap angle. So of course we will not go into much details now at the moment. Okay, now it is important that whatever the theory we have studied, how we can implement it for practical conditions. So to practice that we will be solving some of the numerical problems. Okay, so first numerical problem we have is, we have a sharp flat plate with its length equal to 1 meter and width of the plate is 3 meters, and it is immersed parallel to a stream of velocity 2 meters per second. So it means that velocity, free stream velocity, so capital U over here is nothing but 2 meters per second, and we need to find the drag on one side of the plate. So whenever a plate is immersed in flow stream, so plate can have drag on the upper face as well as on the bottom face, but it is given in the question that we need to find the drag only on one side of the plate. So first task is we need to determine the drag, and second task is at the trailing edge find the thickness delta, delta star and theta. So means we need to find the boundary layer thickness, displacement thickness and the momentum thickness at the trailing edge of the plate, and this we need to do by using two different fluids. So first fluid is air, for which density is 1.23 kg per meter cube, viscosity is 1.46 into 10 to the power minus 5. Sorry, this is not mu, this is nu, because unit is meter square per second. So this is the kinematic viscosity, not the dynamic viscosity. Okay, so this should be nu, and for water density is 1000 and kinematic viscosity nu is 1.02 into 10 to the power minus 6 meters squares per second. Okay, so the very first thing what we need to do is we need to understand first whether the flow over the plate is purely laminar or is it the combination of laminar and turbulent flow. So for doing that, what we will be doing, we have to first calculate the Reynolds number at the trailing edge of the plate. Okay, so if I calculate Reynolds number, then it will be rho VL by mu, and mu by rho is nu, so V into L by nu. So if I calculate this Reynolds number, it is coming out to be 1,37,000. Okay, and what is the critical limit above which we will be finding transition to turbulence? If we have smooth plate, then it will be 3 into 10 to the power 6. If we have rough plate, then 5 into 10 to the power 5. Okay, so it means my flow is purely laminar. If flow is purely laminar, then I need to determine now the drag coefficient. Okay, so drag coefficient, now I need to use the relation which is given for the laminar theory. For laminar theory, what was the relation? 1.CD equal to 1.328 divided by square root of Reynolds number once it is calculated based on the length. So that is something which I have done over here, 1.328 by Reynolds number raised to power 1 by 2. So this is now my drag coefficient. Okay. Once I have the drag coefficient, then drag force will be equal to CD times half rho u square into plane form area. So plane form area will be B into L for a flat plate. And from here you will be finding that 0.0265 newtons of drag force is actually acting. Okay. Then second question is you need to determine the boundary layer thickness. Okay. So for laminar flow, we know that delta by x equal to 5 by Rex square root. Okay. Now we need to calculate the boundary layer thickness at the trailing edge. So for trailing edge of the plate, x will be equal to L. Okay. X will be equal to L. So that's why delta by L will be 5 by Reynolds number, and this is 0.0135. So from here delta is 13.5 mm. So you can see that for a plate of 1 meter length, the boundary layer thickness at the trailing edge is 13.5 mm. Okay. And delta star, which is the displacement thickness, that is 4.65 mm, and theta is 1.79 mm. And of course the relations for all I have given. Delta star is 1.721 by 5, and theta they have calculated from the flow safe factor, because flow safe factor, which is theta by delta star, is equal to 2.59. Okay, so that's why from it we are calculating theta. Is this point clear? So first part is done. Now we need to do the same analysis once we change the density to water density and viscosity to water viscosity. Okay. So upon doing so, we will be finding that our Reynolds number is 1.96 into 10 to the power 6. If I assume that my plate is smooth, then my transition Reynolds number is 3 into 10 to the power 6. So this is still smaller than transition Reynolds number. So once again I will be considering the flow is laminar flow. Once the flow is laminar, then again same relations I will be using. So my CD is this, and this is the magnitude of the drag force now, 5.70 Newton. Okay, and if you see the boundary layer thickness, it is 3.57 mm. Is this point clear? So now boundary layer thickness has become even more thinner. Are you understanding this point? For air, boundary layer thickness was 13.7 mm, and for water, boundary layer thickness is only 3.5 mm. Okay. Can you relate this to physical understanding of the flow? When you are moving from air to water, you are going towards higher viscosity. Once you have higher viscosity, you will be having the faster diffusion of the momentum. Once you have faster diffusion of the momentum, you will be having the presence of thin boundary layer. Okay. Then delta star is 1.23 mm and theta is 0.48 mm. Now let's attempt the same problem. We will be attempting the same problem by considering that transition Reynolds number is 5 into 10 to power 5. If I consider my transition Reynolds number is 5 into 10 to power 5, then what will be happening? My flow will be turbulent at the trailing edge, but laminar in the front portion. So it means it is a combination now of laminar as well as the turbulent flow. Okay. So once we have the combination of laminar and turbulent flow, then what will be my CD? I need to use the CD relation which accounts for both the laminar and the turbulent effects. So what is the value of CD? I have given you in the last class. What was the value of CD? Okay, so you try by your own. I will not do this. Fine. So the same question can also be done if I set my transition limit as 5 into 10 to the power 5. Then you have to choose the value of CD which is accounting for both the laminar and the turbulent effects. Yesterday I have given you that relation. Okay. And once you calculated CD, you can determine this. Once you have done so, now can you tell me what will be these three parameters? Now when I will be calculating these three parameters at the trailing edge, these three parameters I need to calculate from the relations of the turbulent flow. Okay, because my Reynolds number is 1.96 into 10 to the power 6, which is greater than 5 into 10 to the power 5. Okay, so that's why I need to now apply for the trailing edge for calculation of all these parameters the relations of turbulent flow. One important question can also come from this point. Can you tell me how much portion of the plate is having laminar flow and how much portion is having transition and turbulent flow? Can you determine this? This is very simple. You know this transition Reynolds number limit. So transition Reynolds number limit you can equate to rho v some x transition value divided by mu. You have this, so from here you will be able to calculate x transition. So x transition will represent the length portion of the plate at which the value of Reynolds number is reaching equal to 5 into 10 to the power 5. So it means that is the point up to which my boundary layer is laminar and after that the flow is turbulent. All are clear with this idea? Okay, let's talk about problem number 2. In problem number 2, we have a high-speed car with its mass equal to 200 kg, and for car already the drag coefficient is given, which is 0.3, and corresponding to this drag coefficient the effective area of car is 1 meter square. This deploys a 2 meter parachute, so it is having a parachute of diameter equal to 2 meters to slow down from an initial velocity of 100 meters per second. So car was moving at 100 meters per second and a parachute was connected to it of diameter 2 meters, and this is used to slow down the car. Assuming constant CD. So car is having constant CD and for parachute also, though velocity is varying, but we will be considering the constant value of the CD. Brakes free. It means no brakes are applied from the car. And no rolling resistance. It means this friction is also negligible between the tires and the road. We need to calculate the distance and velocity of the car after 1, 10, 100 and 1000 seconds. So what will be velocity and what will be the distance which car has traveled after these many seconds. And of course, in the surroundings of the car and parachute, we will be having air having density 1.2 kg per meter cube, and viscosity should also have been given. So viscosity we can consider from the previous problem. Okay, so viscosity is in the previous problem for air is 1.46 into 10 to power minus 5 meters square per second. So this value will be chosen here as well. And near interference, neglect interference between the wake of the car and the parachute. So after this, whatever the streamline is coming and interfering with parachute, that interference actually we are neglecting. Is this one clear? So how to do this problem? Solution is already given over here, so you can clearly see. First, what we have done, we have written the equation of motion for this. So equation of motion is all the forces which are acting, that will be equal to mass into acceleration, so m into dv by dt. And what are the forces acting? First is drag force acting on the car, so minus Fc, and drag force acting on the parachute, that is minus Fp. Other than these forces, there is no other force acting. Okay, so this is equal to, how drag force we write, half rho v square, so minus half rho v square into CD of car times area of car and CD of parachute times area of parachute. All are clear with this idea? Now from here, what I have done, this combination of CD into A into rho by 2 means this value and sum of these CD into A, this I have written some constant K. Okay. So from here I can write that dV by dt equal to minus K by M into V square. Fine. Now, if I need to find that what will be the velocity after some time, then of course I need to integrate this equation. So I have integrated dV by V square from V naught initial velocity to any velocity at V at time t, and minus K by M integration of dt from 0 to t. From here you will be finding that your velocity naught minus 1 minus V of minus 1 equal to minus K by mt after integration, and you can say that your velocity at any time t is equal to initial velocity divided by 1 plus K by M into V naught t, where K is this value. That already we have. Is this one clear? So it means that if I know the value of K, M is given for the car, V naught is given for the car, and T is given to us at what times we need to calculate the velocity. So only thing I need to calculate is K. For calculating K, I need CD of the car and area of car, which are already given in the question. But what is not given is CD of parachute and area of parachute. So for that, what we will be doing, just now I have shown you one table. So this is the condition. Based on the frontal area of the parachute, if we calculate value of CD, then it is 1.2 for a parachute. Okay. So it means that my CD parachute is equal to 1.2, but what will be its area of parachute? Now it is given in the question that the CD of the parachute is based on the frontal area. Okay, so frontal area of parachute, if diameter of parachute is 2 meter, then its projection, which is normal to the flow stream, that will be this, and this is the frontal area, which will be pi by 4 into dp square. So that will be frontal area of the parachute. All are clear with this idea? So now you can see that S, if you need to calculate distance, then of course once again you need to integrate, because you can write velocity as ds by dt. So in the previous relation, this velocity you can write as ds by dt, and once again you can integrate this equation to calculate the value of S. and if you do so, you will be getting S equal to V naught by alpha into ln of 1 plus alpha t, where alpha is nothing but K by M into V naught. So this alpha we have used for the purpose of integration. Okay, but how we have done this? So we have written ds by dt, and once again we have integrated this equation, and this K by M into V naught we had written alpha, and if we integrate this, then this will be my expression for S. Okay, so now CD for parachute is 1.2. So now I need to simply substitute over here these values to calculate K. So this is the value of K, 4.07 meters square, and K by M into V naught if I calculate, that is my alpha, 0.122 per seconds. So now you can see at time 1, 10, 100 and 1000 seconds, these are the velocities and these are the distances. So it means that if you consider that rolling friction resistance is neglected, brake is not applied, only parachute is allowed to stop the car. In that case, if car is moving at 100 meters per square and parachute is of 2 meter diameter, then you can see it has already traveled a distance of about 3.94 kilometers before stopping. So it means parachute sufficient as a standalone cannot completely stop the fast moving car. Are you understanding this point? Because, so if you consider here what is happening, because the mass of the car is too high, so it will be having significant inertia. Okay. So because of that, it will not be able to stop the car for a huge distance. But of course, in reality, if you go, then you will be having rolling friction also. Okay. Even if you don't apply brake, then because of the rolling friction also, this distance will be significantly reduced. Okay. All are clear with this idea? So based on the flow past immersed bodies, you may get this type of numerical problems. Okay. So with this we close our course, and if you have any questions that you may discuss,